In this video, we are going to talk about the relationship between two variables, right? Last time we talked about whether a dependent variable and the independent variable have a linear relationship or not. If they have, what is the correlation coefficient? What is the trend line that goes through the most of the data points? How do we estimate them? And then how do we do the hypothesis testing, right? Even though the uh, even though the sample regression coefficient of the sample is different from zero, sometimes the regression coefficient in the population may not be different from zero, right? Meaning they may be the population correlation coefficient may be zero. That means there may not be a linear relationship between x and y variable. In the correlation, though, we don't have a dependent and independent variable. We don't care that much because the correlation coefficient between x and y and x are the same. Okay, in correlation we find out the measurement of the relationship. Okay, we will measure the relationship between the two variables. So correlation is a statistical method used to determine whether a linear relationship between variables exists. If a study contains two variables, correlation measures the relationship between two variables and their strength. So it also studies the strength between the relationship of the two variables. Okay, in this case, one variable is called independent variable and the other is called dependent. So for a study with more than two variables, correlation measures how the variables are related. In this case, there are more than two independent variables. Scatter plot is a graph of order pairs. So we know the scatter plot already. We just plot x and y, right? So the correlation coefficient is the formula for this is the formula for the sample correlation coefficient. For sample correlation coefficient, we denote by R. For the population, we denote by rho. Okay, we say RHO. Rho is that for the population correlation coefficient. This is the formula for the sample correlation coefficient. You will have x and y given. So you find out x times y and then find the sum of x, sum of y, and then find out x squared and y squared and sum of x squared, sum of y squared. What is n? N is the number of order pairs. Okay, number of pairs. So this is what we do. You see that? So this is the alternative definition of that, but don't worry about that one. Just we'll be writing in this different format on that. So let us see the interpretation of the correlation coefficient. If R is close to positive 1 or negative 1, then the relationship is strong. Okay. If R is close to 0, the relation is weak. If R equals to 0, there is no relationship. Okay. To find out R using calculator, this is how we use the calculator. But how do we use R to find out the correlation coefficient? Okay, let us find out the correlation coefficient of this data point. We have the x is given, okay, and the y is given. So x is let's read that. An environmentalist wants to determine the relationship between the number of forest fires, that is x, over the year and the number of acres burned. Okay, so y is the number of acres burned and x is the forest fires. Okay, so now you want to find out the correlation coefficient between those two. So how do I find out using R? Let me show you how do I find the correlation coefficient using R. So this is the x data, okay, and this is the y data. So what I did first is I want to plot the scatter plot. You see that x is the forest fires and y is the number of acre burns. Okay, so when it increases, you see that the value of y is increasing. So it looks like there is a linear relationship between x and y. So what I want to do is I want to find out the correlation coefficient, sample correlation coefficient. Also, I want to test whether that correlation coefficient is significant in the population or not, right? What that means is are the x and y related or not? Is there a relationship between x and y in the population or not? Okay, so let me run that, and then let me run that one. What it says is this is the sample correlation coefficient, R. This is the R value, and when you try to test the correlation coefficient for the population, you see the p-value. The p-value is 0.02526. What does that mean? p-value, that means you reject the null hypothesis. So what is the null hypothesis? Null hypothesis is rho equals to 0, meaning there is no relationship. So alternative hypothesis means x and y have relationship, right? So it support the alternative hypothesis, meaning that there is a linear relationship between the number of forest fire and the number of acres burned. Okay, so we will go over each and every steps of how to do the hypothesis testing of the correlation coefficient by hand. But we will do by hand. I will just go through the steps of that. Okay, so this is how we find out the correlation coefficient for this. Okay, so unlike the regression, you see that we are trying to find out the correlation coefficient between x and y. We got that the sample correlation coefficient is 0.77050, right? If you do y and x, this is what you get. You get exactly the same result here. You will get exactly the same result. So the hypothesis testing, or the basically the confidence interval, this is the 95% confidence interval for the correlation coefficient, and the sample correlation coefficient will be the same whether you take x comma y or y comma x. Okay, so we are not concerned about which one is dependent, which one is the independent variable here. We are just testing the relationship between x and y or y and x. Okay, let's see the steps of the hypothesis testing for that. So what we do is 80 is rho equals to 0. Rho equals to 0 means the correlation coefficient in the population is 0, meaning x and y are not related in the population, versus x and y are related in the population. To find out the critical value, we use the t-test, two-tail t-test, okay, with n minus k minus 1 degrees of freedom, where k is the number of independent variables. Step 3 is find the correlation coefficient use a calculator and find the test value. This is the formula to find the test value. First of all, we need the value of r. From calculator or from R programming, you find out the value of R, and n is the number of pairs. Okay, and n minus 2 over 1 minus, this is for the two samples, two variables x and y. Okay, if there are more than two variables, then it is n minus k minus 1. All right, step 4 is make the decision. So you know the n minus 2 is the degrees of freedom for this case, because k will be k is the number of independent variable, right? If there is x and y, if there is x and then y, so the k is equals to 1, right? K is equals to 1 because there is only one independent variable. This is the dependent variable. So that's why the degrees of freedom goes here, n minus 2. So step 4 is make the decision. If there are more than two variables or more than one independent variable, so we usually use the software to find out to test the correlation between two variables. Okay, next is the make the decision, decide whether the test value falls within the critical region, summarize the result. Okay, so also the confidence interval. So instead of 80 is rho equals to 0 versus rho not equals to 0. If you are testing a hypothesis for rho equals to some number versus rho equals to not equal some number, or less than or greater than, the above formula is not useful. You see that? If you are setting rho equals to 0 versus rho not equals to 0, then above formula is useful. But if you have rho equals some non-zero number, or not equals to some non-zero number, less than greater than, then the above formula is not useful. For critical values, we use z-test for the given alpha and the statistics. This is what we use. Okay, where z is given by that, r is the correlation coefficient of the sample, zeta 0 is given by that. Okay, rho 0 is basically whatever value you are testing there, and sigma g is 1 over n minus 3, and n is the number of pairs. So for the confidence interval, we use this formula, but when you use r find out all those things straight right away. Okay, so this is the example that I did by hand. Again, you can do this example by r, which will be easier and faster to do that. And there is another example. So what is the difference between those two? So here we are testing the correlation coefficient, comparing the correlation coefficient between, let's say, listed below are the temperature, degree Fahrenheit, and the number of times the cricket chirps in 1 minute. Okay, for alpha equals 0.05, is there a significant evidence to conclude that there is a linear correlation between the number of chirps and the temperature? Okay, this is the example. So you can do this example by R. Okay, so on this slide actually I'm going to talk about if there are more than one correlation coefficient. For example, if you are comparing the two correlation coefficients, rho 1 and rho 2, they are equal versus they are not equal. So this is how you do it, and this is an example to do that. Okay, so you can follow this example. So basically these things are given here. Okay, so in the first example, so for the test statistic you use this formula where gi is given by that, and sigma is given because you see that sigma subscript g1 minus g2 is given by that formula. Critical value is the g alpha. We use the g table or the p norm, right, or q norm. Decision and conclusion. So you see that for a sample of 98, so n is 98, right, bird wings and tail lengths are equals to 0.78. R is given. A sample of 95 such measurements from a second bird species yielded R equals to 0.84. So we are testing whether these two are equal in the population or not. You know, because you see that this is one sample. From one sample they calculated that, from another sample they calculated that, and we want to test whether the both sample are giving the same result or not. Okay, test whether the two correlation are equal in their population with alpha equals 0.05 or not. So we use exactly the same steps to do that. Okay, but when we do in the by hand, so you'll have a little bit of calculation there. Note that since the two populations have the same correlation coefficient, you see that whenever you find out the test statistic, you got negative 1.202, and then critical value is 1.96, right? It is two-tail critical value, so it will be plus minus 1.96. So what does it imply? So you do not reject the null hypothesis, because how does that look like? It looks like 1.96 is here and here, right? Negative 1.96, 1.96, and your test value falls here. So this is the rejection reason, right? Your test value falls here, meaning that you do not reject the null hypothesis. So let's look at this note. Since these two populations have the same correlation coefficient, we find their common correlation coefficient using that. Okay, so and then we solve GW equals to that to find out the common or weighted correlation RW. So to find out the correlation coefficient, for example, if there is a population and when you take two different samples and if you find the two different correlation coefficient, so since they were both taken from the same population, you use this formula to find out GW, and then we use this formula. We solve this after we find out GW. We solve this one to find out the common correlation coefficient of those two samples, okay, or the whole population. So if you are comparing more than two correlation coefficient, this is what it looks like, right? Rho 1 equals to rho 2 equals to rho 3, meaning the population correlation coefficient of the three populations are equal versus they are not equal. Test statistics, this is the exactly same formula but extended form. We use that one and we find out the critical value using the chi-square table, okay, and then you decide. So what it says is if H0 is not rejected, then we find the common correlation coefficient using that exactly the same extension. Okay, we can perform multiple comparison among correlation coefficient using 2K type method, which computes the correlation coefficient for each sample versus the other. So let us go about the R first, and then how do I do the things that we just discussed in R, and then we will go over the rank correlation. Okay, let me open that R file. Okay, so by the way, what are the assumptions for the correlation coefficient? The main assumption is the distribution of the sample X and the population distribution of sample X and Y must be normally distributed. That's one of the main assumption for the correlation coefficient. So what I'm trying to do here is I'm trying to find out the simple versus multiple correlation. Okay, so correlation coefficient and hypothesis testing with assumptions. Look at that. My data equals to empty cars. Okay, what type of data is empty cars? So let me run that and then I will show you what type of data is that. Okay, so my data is the empty cars. Empty cars has so many values of the variables here for different types of cars. These are the brand of the cars and the make and model, I think, and then this is MPG, miles per gallon. This is the number of cylinders, displacement, HP, horsepower, DRAT, weight, cubic, V. So there are so many variables here, right? So what you want to do is you want to test the MPG and weight. This is MPG, this is weight, okay? So we want to test whether the MPG depends on weight or not. So let us see an example with the correlation coefficient and hypothesis testing with assumption. So we will see simple correlation, meaning one X and Y, the other one is multiple correlation, meaning that you will try to find out the relationship, evaluate the relationship between all the pairs, possible pairs of the variables, okay? So I am doing the, I'm taking the empty cars data. What is that empty cars data? Empty cars data has all brand of cars here, and the mile per gallon, cylinder, displacement, HP, DRAT, and then weight. All those variables are given here, okay? So what we want to test first is, we want to test is there a relationship between MPG and the weight of the car, okay? So what I'm trying to do here is I want to first check whether the MPG data is normally distributed or not. So when I do that, I got that the p-value is 0.1229. That means we do not reject the null hypothesis, meaning that the variable is normally distributed. Let me test for the weight data. The weight data is also normally distributed because p-value is greater than alpha, okay? So what is the null hypothesis is the variable is normally distributed versus the alternative hypothesis is variable is not normally distributed, okay? So in this case, the variable is, both of the variable, MPG variable and the weight variable are normally distributed. Now let us plot how does it look like the data. See, you see that whenever the weight increases and the miles per gallon, the mileage decreases. You see that? This is what the data said. Now I want to know I want to do the hypothesis testing. Is that the correlation? What is the correlation coefficient of the sample? And is there a relationship between weight and MPG in the population? Okay, that's what I ran. Result equals to correlation dot test. This is the X data or Y data, and this is another data, X or Y. Okay, method is Pearson. So this is the Pearson correlation coefficient. That's what it is trying to find out. Let me run the result, and it will give you what is the p-value. P-value is less than alpha, right? Meaning that we reject the null hypothesis. What is the null hypothesis? Null hypothesis is rho equals to 0, meaning there is no relationship. Versus the alternative hypothesis is there is a relationship between X and Y. So it says that it supports the alternative hypothesis, right? So that means there is a relationship between X and Y, or the mile per gallon, the mileage and the weight of the car. You see that this is the 95% confidence interval, which does not include 0. You see that? So also the correlation coefficient here is negative 0.86. That's what you got. So let us see the t-test. So this is basically a description about what we output we got. T is the t-test statistic if you do by hand. DF is the degrees of freedom. P-value is the significance, right? Confidence interval is the 95% confidence interval. And then sample estimate is this is the correlation coefficient of the sample. Okay. There is another method of finding the correlation coefficient. This is called the rank based. It is called Kendall's method. Okay. So it will give you the same output. I mean the result will be the same. You see that the p-value is less than alpha, still less than alpha, so you do not reject the null hypothesis. And then sample estimate for the correlation coefficient is that was given. So it is using slightly different methods. So it is using the rank of the data, not the real data. Okay. So for the multiple correlation coefficient, what do you have is you will have y and then x1, x2, x3, x4, x5 like that, and then you will try to find out the relationship between each of those variables. For example, what is the relation between y and x, y and x1, y and x2, y and x3? Similarly, x1 and x2, are they related or not? x2 and x3, and so on. Okay. So for that, you will have to install the package psych. Okay. And the data, we are taking exactly the same data. So empty cars. So I am collecting all the rows and only 1, 3, 4, 5, 6, and 7th column. So I'm selecting only few columns from that data. This is what the data looks like. Okay. So previously we had a bigger data because we had many columns. Now I pick only 1, 2, 3, 4, 5, 6. 6 columns only. 1, 3, 4, 5, 6, 7. These columns only. So now I want to test the correlation between all those. What does that mean? That means correlation between MPG and displacement, MPG and HP, MPG and DRAT, and similarly displacement and HP, displacement and DRAT, and all those different combinations. So it will find out the correlation coefficient of all combinations of these variables. Okay, let us do that. When I do result 1 equals to correlation and then my data, that will give you the result 1, that is the correlation coefficient. What does that mean? The correlation between MPG and MPG is 1, so we are not interested on that. We are interested on MPG and displacement is negative 0.84. MPG and HP, horsepower, is that. And MPG and DRAT is that. MPG and weight is that. MPG and QSEC is that. Okay, or you can see this way: MPG and displacement, MPG and HP. So it will give you basically 2 results. So you don't need all of them. Okay, this is what you will get. So if you want to round up these values, so what I did here is round result 1 with 2 decimal places. Okay, that's what I am doing here. Okay, when I do that, you can see it better way. So it looks like some of these variables, for example, displacement is negatively correlated with MPG, meaning when the displacement increase, MPG will decrease. Similarly, horsepower is negatively related, meaning when you increase the horsepower, you will decrease the mileage, right? DRAT is positively related, but we don't know whether that is statistically significant or not. We'll have to find out the p-value for that, which we will do next. But from that you can see that since these correlation coefficient, sample correlation coefficient, are close to 1, we assume or we expect that they are significant. Okay, similarly weight is inversely related, meaning that when you increase the weight, then the mileage will decrease. And QSEC is, it is always small but positive, meaning that when you this increase, then MPG will increase. So you can see all those values basically repeated there. If you want to know the correlation coefficient between displacement and HP, look at that, displacement and HP. You look at this one, displacement and DRAT, displacement and weight, displacement and QSEC, and so on. Okay, now if you want to know the p-value also, significance, to test the significance, you will see that you will run this. Okay, you will run psych and then double column correlation.test my data. That's what you will do. You see that when you run this one, and then run this one, it will give you the R values. That's what exactly we got previously. But if you do that $sign and then P, it will give you the P value as well. So this is for MPG, this less than alpha. So this is significant. This is less than alpha. All of these are less than alpha, right? And this one is 0.01. This is also less than alpha. So all of these are significant. You see that? And similarly for displacement, MPG is significant. This is also, all of these are significant. For HP, all of these are significant. For DRAT, all of these are. So basically this one is not significant. For DRAT, QSEC is not significant. You see that? Because it is 0.6, right? Or 0.06, right? 0.06. I think this is this over 10. So 0.6, not 0.06. This is 0.6. So 0.6 means which is greater than alpha. So DRAT and the QSEC are not related to each other. There is no relationship between DRAT and QSEC. Similarly, you can do the other one. Okay, this is what it means. Now, so I want to do everything in the same plot. How do I do that? What do you mean by everything in the same plot? So I want to plot all those, whether they are normally distributed or not, whether what is the correlation coefficient, how does the scatter plot look like, what is the p-value, all those things in the same plot. For that, you will have to install a package performance analytics. Okay, and then you call that library. So if I do that, this is the data that I got. I already defined that data, 1, 3, 4, 5, 6, 7 column of the empty cars data. And if you do chart.correlation, this is what you get. Okay, you see that? For MPG, this is what the data looks like. Okay, and this is what the data normality, whether it looks like almost normal, right? And this is MPG versus the, what was the first one? Displacement, right? So you see, MPG, this is the first column, this is the second column. You see on that data set, first column displacement, HP, all those things, right? What does that mean? That means this is the relationship scatter plot between displacement and MPG. Displacement, MPG. This is the scatter plot. All right. and you see that it looks like a negatively related. Okay, and what it says, this is the p-value between those two. This is the p-value between those two. What is this one? Okay, let's say this one. This one is the correlation coefficient between MPG and HP. You see that? HP and MPG. And what is this one? This is the scatter plot for MPG and then HP. This is the scatter plot for displacement and HP. You see that? What are these other values? This is the sample correlation coefficient of the MPG and DRAT. This is for MPG and weight. This is for MPG and the QSEC. You see that? Okay. So this is how you can see everything, almost everything in the same plot. That's what. So you can see the description here. So the distribution of each variable is shown on the diagonal. On the bottom of the diagonal, the bivariate scatter plot with the fitted line are displayed. Okay. So it looks like they're almost linear. They're almost linear, almost linear. Sometimes you don't see the linearity, but here it looks like this is not very linear, right? The relationship is not, and this one is not very linear. But in almost all of those cases, I see the linear relationship there. Okay, so the p-value determines the significance. Okay, so what is this? Let me check whether it runs or not. If it does not run, never mind. Okay. So what are the assumptions? So these are the assumptions. The variable must be either interval or the ratio measurement. Okay, the variable must be either the ratio or the interval measurement. The variable must be approximately normally distributed. We did that already. There is a linear relationship between the two variables. That's not really an assumption, but yes. And then outliers are either kept to a minimum or are removed. If there is any outlier, you remove or keep it in the minimum. There is a homoscedasticity of the data, similar variation for the y along x values. For any x values, the scatterness of the y values must be similar to almost all of those. So this is how we do the simple versus the multiple correlation coefficient. All right, guys.